Okay, so in this video we want to look at sums and products of functions. So sometimes a function might be the sum of two other functions. Many functions are the sum of two other functions. Any polynomial, well not any, but lots of polynomial functions, x squared plus 5x, that's a sum of x squared and 5x. We could think about those as two separate functions and think about adding them together to produce a resulting function. Now we wouldn't for a simple example as that, but more complex examples where a function is the result of adding together or subtracting, because we can rewrite a subtraction to think about it as an addition. If we're adding or subtracting two functions, we can use this technique called addition of ordinates to sketch the function. Now I'm going to do this for a really simple example where we know what we're expecting the graph to look like, just to show you how it's done. But the point is that this technique is going to enable you to sketch by hand, albeit, a sort of rough sketch, what a function that you might not otherwise know about looks like. So if we ever think about this simple function, x squared plus 2x, we could think about that as the sum of two functions, f of x equals x squared and g of x equals 2x. So addition of ordinates allows us to use the graphs of y equals f of x and y equals g of x to sketch the graph of their sum. Now, I've drawn up a table of values here. I'm not advocating that you draw up a table of values. That would defeat the purpose. It wouldn't make this an efficient process, okay? But I want you to see numerically what I'm doing graphically as I look at each point. So I draw the two separate functions, y equals x squared and y equals 2x. And I want to draw the graph of x squared plus 2x by thinking about adding the ordinates. Now, ordinates, coordinates, we know about. The ordinate is the y values. So we're going to add the y values because that is what happens. If you want to know when x equals, when x equals 1, what does x squared plus 2x equal? Well, you work out what x squared equals, it equals 1. You work out what 2x equals, it equals 2. And so therefore x squared plus 2x will equal the sum of those two separate y values. Okay. So we want to be able to do that graphically though. So we want to be able to, for example, you would pick an x value. We'll talk about that there's some that you want to look at that are key points that are useful. Pick any x value. So let's go with x equals 1 because we were just talking about that in the table. We can see that x squared is equal to 1 and 2x is equal to 2. So when we add together 1 and 2, we're going to get 3. The sum is going to go through the point 1, 3. Okay. You essentially are adding up that y value plus that y value to get that y value. Sometimes I like to think about it as taking that y value and adding it on to the other graph, okay, to work out where we go, because it's not always going to be as perfectly precise numbers. We can pick another x value when x is equal to 2. We can see graphically here both functions have y values of 4. So when we add together those two functions at x equals 2, we'll be doing 4 plus 4. We can see that in the table here. X squared is 4, 2x is 4, therefore x squared plus 2x is 4 plus 4, which is 8. So it's going to go through this point at 8. When x equals 3, okay, the y value of the straight line is 6. The y value of the parabola is 9. 6 plus 9 is 15. Now once again, you don't even need to know precisely what those values are. You essentially want to take this height, which we know is 6, and add it onto this height, which is 9. So I like to think about kind of taking this, let me see if I can sort of demonstrate this here, taking this much height and adding it on top of the other function. Okay, that's essentially what we're doing. Oops, sorry, I need to do that. That's essentially what we're doing. So it's going to go through there. When x equals 4, again, without working out those actual numbers, this height here is going to get added on to the other graph. And so we're going to be actually off the chart. We can see from the table of values we're doing 16 plus 8, which is 24, which is off the chart here. Okay, so and we continue to do that for various x values until we're happy that we've got a sense of the shape of the new graph. So when x equals 0, both separate functions, x squared and 2x, both also equal 0. 0 plus 0 is still 0. Okay. When x equals -1, the parabola is equal to positive, or the y value of the parabola is positive 1. The line is negative 2. 1 plus negative 2 is negative 1. Okay. So again, you might think about, okay, well, I've got that much height. I need to add that on to the other graph. Oh, sorry, I didn't get the whole thing. Let me try that again. I need to add that onto the other graph, and so it's going to go through that point at negative 1. Okay, again here at negative 2, we've got that much positive y value, which we're going to need to add onto the other y value, and we find, we get to 0. So here, because the two graphs are equidistant either side of the x-axis, it's positive 4 plus negative 4, so that's where the graph's going to go through the x-axis. Here we've got, you can think about it the other way around, that much negative that we're going to need to therefore take off the other graph because you're adding on a negative. Okay, so you can think about it that way, or you think about it as you've got this much positive y value that needs to get added on to the other y value to bring us to this same point here. Okay. Again, you've got this much y value that needs to be added on to here to bring us there. Okay, and so we've now got a series of points. I'm just thinking they should be symmetric. Which one's not right? Sorry, I think I added this one on wrong. Let me try that again. So this is 16 and this is negative 8, so it should be at positive 8. Sorry, I just misjudged that slightly. Alright, so the sum of those two functions, x squared plus 2x, is this new function here. Now I deliberately chose a function that we already know what that looks like anyway. If I'm trying to sketch the graph of x squared plus 2x, x is a common factor, x plus 2, it has x-intercepts at x equals 0 and x equals negative 2, which is exactly what I'm seeing in the sketch. The point is this process of addition of ordinates enables us to think this through for other functions. So as I said, I don't want you to have to calculate all the various y values. That defeats the purpose. It's a graphical process. You want to be able to look graphically at roughly what the two y values are, think about adding those together and therefore working out where your new point is going to be. Alright, let's have a go at doing that this time without having the table of values. So we want to sketch the graphs of f of x equals 1 on x and g of x equals x to hence sketch the graph of f plus g of x. So f plus g of x means f of x plus g of x. Okay, so let's draw f of x, and we want to draw it quite precisely so that we can, our addition of ordinate, we can be using the same scale for both graphs, and we can add the ordinates a bit more precisely. So I've given you a grid here, so let's plot it precisely. So 1 on x goes through 1, 1, goes through 2, 1/2, 4, 1/4, half 2, 1/4, 4, okay. So something like that, and then the mirror image over here, -1, -1, -2, -1/2, -4, -1/4, -1/2, -2, -4, -1/4, -4. Okay, so there's our hyperbola. Oops, not 1 on 2, 1 on x. And then just the line y equals x, so that's nice and easy. It's going to go through 1, 1, 2, 2, 3, 3, 4, 4, -1, -1, -2, -2, -3, -3, -4, -4. Okay, and now we want to add the ordinates. So I should have said, let me go back to this original example. So there's some key points I'd be looking at first. I'd be looking for places where the two graphs intersect. Okay, they're nice and easy because you just double the y value. Where the two graphs intersect, 4 plus 4 was 8, 0 plus 0 was 0. Okay. Other things I'd be looking for is where one graph has an x-intercept. In this case, we've only got that happening there. But if one graph has an x-intercept, that means its y value is 0, and so you'll just go through the other graph. Other places you'll be looking for will be places like this, where the graphs are symmetric either side of the x-axis, because that's where your addition graph, your sum graph, will have an x-intercept. So trying to sort of look for those key points. The other thing I'm noticing here with this example is when x equals 0, the hyperbola doesn't exist, and so therefore the sum of the line and the hyperbola can't exist either. Okay. Alright, so let's just pick some points. So let's have a look at when x equals 1. Okay, we can see y equals 1 for both functions, which means that when we add 1 and 1, the graph will go through y equals 2. Okay. Let's have a look at when x equals 2. So we do know the values here. The linear graph's got a y value of 2 and the hyperbola has a y value of 1/2. So the sum will go through 2 and 1/2. But again, graphically, even if you don't know those values, it's still about thinking, right, I've got this much height that I've got to add on to this other one if I'm going to add together their y values. Okay. Try again. I'm just going to redraw in that black line instead. Okay, so 2 and 1/2 here. Okay, then we know we're going to be adding a third onto the line, and then we're going to be adding a quarter onto the line, adding 1/5 onto the line. So the graph's going to get closer and closer and closer to the line y equals x, because the y value of the hyperbola gets closer and closer and closer to 0. Okay, if we think about here, perhaps when x equals 1/2, on the straight line graph, the y value is 1/2. On the hyperbola, the y value is 2. So that's going to be at 2 and 1/2. Okay. And obviously, as the straight line's getting closer to 0, the y value on the straight line is getting closer to 0, and so therefore the purple graph is going to be getting closer to the hyperbola. And then it's undefined at 0. So we've got that kind of shape happening there, and we've got nice symmetry here, so we should be seeing the same thing happen here. Closer and closer to the line there, and then closer and closer to the hyperbola there. Okay, and we should be able to check that. Let's have a look at the graph of 1 on x plus x. Yeah, that's pretty good. Okay, so I'm not saying you're going to be able to draw a perfectly precise graph, but you still should be able to, think through a rough sketch of what it's going to look like. So our purple graph is y equals 1 on x plus x. So in this case, the domain of f, the hyperbola, is all the real numbers excluding 0. The domain of g, which is the straight line, is all the real numbers. The domain of f plus g, both of these functions f and g have to exist in order for you to add them together. So it's always going to be the intersection of the two other domains. Okay, so it is the domain intersection of the domain of f and the domain of g, which in this case is excluding 0. Alright, here we want to use addition of ordinates to sketch this graph. Now we've got a subtraction here, but what I want to think about is I instead want to think about this as being, so it's y equals the square root of x plus 2 minus x cubed on 2, but let's think about that as the square root of x plus 2 plus negative x cubed on 2. So we're going to draw this graph as a reflected graph so that we can still add the ordinates, otherwise it gets too complicated. Okay, so square root of x plus 2 is a square root graph translated to the left by 2. So it's going to start here. You can sub some points in. When x equals -1, we're going to have square root of 1, so it goes through -1, 1. When x equals 0, we've got root 2, which is about 1.4. When x equals 1, we've got root 3, which is about 1.6. When x equals 2, we've got root 4, which is 2. Okay, root 5, I don't know roughly what that is, but that's okay. Root 6 also, still going to be somewhere between 2 and 3. So we're going to have and then we're going to have negative x cubed on 2. So it's going to be, this kind of cubic, but let's draw it precisely. So it's going to go through 0, 0. When x equals -1, it's going to be positive half. When x equals -2, negative 2 cubed is -8, but make that negative is positive 8 divided by 2 is 4. Okay. and the symmetry there, this will be down to 4 down here just to get the shape right. Okay, so there's our two graphs. We now want to use addition of ordinates. So this graph exists back here when x is less than -2, but this graph doesn't. Okay, so there's not going to be any, you can't add the two graphs where they don't both exist. Let's start here at this endpoint when x is -2. It's an x-intercept for the square root graph, so the y value there is 0, which means if we add that 0 y value onto this other y value, we're just going to go through that point. Okay. The two graphs are crossing here just a little bit less than 1, so when we add up, when we double a number that's a little bit less than 1, it's just that bit more less than 2. Here this is 1 plus a half, so that's going to be 2.5, so it's going to look something like that. Here at x equals 0, the y value of the cubic is 0, and so adding together the two y values is just going to go to there. Here I might want to think about, okay, we've got that much negative to take off of this function, okay? So we're going to be going through there, about there. Oops, sorry, I'm on the pen. About there. And then we've got, when x equals 2, it's -4 plus +2, so it's -2. So it's only going to get, the cubic's getting more and more steep this way, where this is getting bigger less quickly, so it's going to shoot off down here. It's a bit tight in here, but let's have a think about sort of what's happening here. So the cubic, between -1 and 0, the cubic is always a positive value, which means we're going to be adding, even if it's small, something positive. So the graph should be sitting above the square root there, whereas here the cubic is negative, so we're taking away from the other graph, so we should be below. Okay, so we're essentially going to get something that does something like, stays above it there, intersects it there, and then is underneath it, and then it's going to shoot down here. Okay, there'll be somewhere here where they're roughly the same distance either side of the x-axis, which will mean that's where we get an x-intercept. Okay, and it's going to look something like that. Let's have a look. Alright, so what's our function? Square root of x plus 2 minus x cubed on 2. Yeah, pretty good. Not too bad. State the domain of this function. Okay, so remember the domain of f plus g is equal to the intersection of the domain of g and the domain of f, because they both have to exist. The domain of f is from -2 to infinity inclusive. Domain of g is r, so it's just the domain of f that applies then. -2 to infinity, sorry, not inclusive of infinity, inclusive of -2. Okay, a function might also be the product of two functions, such as f of x times g of x. The product of f of x and g of x would be called fg of x. And we can use a process similar to addition of ordinates to sketch this function. This isn't as common a process, we won't see this as often, so we'll just have a look at one example of this, I think. Oh no, we'll do two. Okay, so again, we've got a table of values here for the first one. So we're going to look at sketching 2x times the square root of x plus 1 we've got those two separate graphs here. So this is the square root of x plus 1, and this is 2x. And we're going to think about this time not adding the y values, but multiplying the y values. Okay. So for example, here when x equals -1, the y value of the square root graph is 0 times -2. Well, 0 times anything is 0. So the product graph is going to go through 0 there. Here, when x equals 0, we've got 0 times 1, which is also 0. Okay. Here we've got, something a bit more than 1 times something a bit more than 1. Let's go with 1.2 times 1.2 just as a guesstimate. So that's about 1.44. Okay, so remember it's not doubling, it's not going to be this much higher. 1.2 times 1.2 is about 1.44. So it's only going to be about there. Okay. Here you've got 2 times this value, so you're going to double this value, whatever this value is. We're going to double that. So it's going to be up there, just a bit less than 3. Okay. Here we've got, 4 times this value, so that's going to be way off the charts. Okay. If you take that and multiply it by 4, you've doubled it, tripled it, multiplied by 4, it's going to be up there somewhere. Okay, so the graph's going to shoot off up that way. Then let's think about perhaps what's happening in between here. So this is -1. So here we're going to be doing that number times -1, which is just going to make that negative. So it's just essentially going to be the mirror image there. So it's going to be sort of down here. Okay. Here we're going to be doing something like, we're going to be making this even bigger than it is. So we're going to be multiplying it by, nearly -2 here. So doubling that, so it's going to be steeper. If you double that, not double it, sorry, because it's about 1.5 times that value. So you sort of just want to try and think about the fact that, but the key thing is, actually, if we think of it the other way, all of these y values up here, they're all less than 1. So we're therefore going to be making sure that our product graph, anything times a number less than 1 is going to make it smaller. So everything's going to get closer to the x-axis here. So I suspect we're going to get something that roughly does this. Okay, let's have a look on our CAS to confirm. Tab 2x times square root of x plus 1. Oh, x plus 1. Yeah. Okay, I'm not asking you for the coordinates of this point. It actually looks like from the graph that it gets lower there, and that point halfway there is not actually the lowest point. But we don't have enough information to really be super precise about that. We just want to get the sense of what's happening, how do the graphs combine together to produce the new shape. State the domain of FG. Again, domain of FG is going to be, the intersection between the domain of f and the domain of g. And that's purely just because both functions have to exist in order for you to multiply their y values together. And so in this case, the domain of g is r, but the domain of f is only -1 to infinity. So that will also apply to the product graph. Okay, sketch the graphs of 1 on x and root x, and hence sketch the graph of fg of x. Okay, so 1 on x is our hyperbola. We drew one of those in earlier. Let me just get a reasonably accurately scaled hyperbola here. So that's a half and a quarter and -2 and -4. Not quite so far out there. Okay, so there's our 1 on x. Root x goes through 0, 0, 1, 1, 4, 2, about 1.4, about 1.6. Okay, so again, we're only going to exist where both graphs exist. So the square root only exists where x is from 0 to infinity. The hyperbola only exists where x is a real number except for 0, and so therefore the intersection of those two things is going to be 0 to infinity, not including 0. So that's just what's written down the bottom here. The domain of f is all the real numbers except for 0. The domain of g is 0 to infinity. The intersection of those two things is 0 to infinity, not including 0. Okay, so not going to have any point when x equals 0, so let's maybe start when x equals 1. Remember, we're multiplying the y coordinates together, so 1 times 1 is still 1, so our product graph is going to go through there. And then we really just want to think about, okay, from here on, the hyperbola is getting less than 1, so we're going to be multiplying by a number less than 1, which means we're making the square root graph smaller. So whatever this value is, we're multiplying it by, half. We're halving it. Okay, so it's half of root 2, which is going to be about 0.7. I've got that half sitting a little high, so it should be above it. This is a third of root 3. root 3 is about 1.6, a third of 1.6 is about 0.5 something. And then, you know, a quarter of 2, well, that's half. So it's going to be getting smaller. It's going to still be going to approach the x-axis here, but it's going to be still sitting above the hyperbola, okay? Now, in this region here, the hyperbola is much stronger than this, okay? This is a number somewhere between, you know, 0 and 1, whereas this is going to get to be a really big number up here. So it's still going to sit below the hyperbola because we're multiplying by a number less than 1, but it's going to get bigger quicker, so it's going to look something like that. Let's have a quick look. So 1 on x plus root x, not plus, sorry, times. Yeah, sort of more extreme hyperbola. If we just do 1 on x for reference on here, yeah, see, it's not as extreme. Well, extreme in different ways. Okay, so what have we noticed about the domain of the sum and product functions? We've talked about this along the way. The domain of f plus g is the intersection between the domain of f and the domain of g, and that's same for the sum, the product function as well, domain of f, intersection domain of g. So if we want to find the implied domain for each of the following functions, we need to think about the domain of that. So we know that x has to be bigger than, x minus 3 has to be bigger than or equal to 0, which means x has to be bigger than or equal to 3. So the domain for that part of the function is 3 to infinity. Here we know that 12 minus x has to be bigger than or equal to 0. So 12 is bigger than or equal to x, which means x is less than or equal to 12. So the domain of f is the intersection of those two things. So 3 to infinity, intersection, negative infinity to 12. If you need a number line to think that through, okay, 0, 3, 12, okay, 3 to infinity is all of those numbers, negative infinity to 12 is all of those numbers. The intersection, therefore, is this bit here, 3 to 12 inclusive. Again, let's have a quick look at this graph to confirm that. So if we have a look at the square root of x minus 3 plus the square root of 12 minus x, we do indeed, let's just change that. We do indeed only see a graph happening between 3 and 12. Alright, if we think about g, if we think about that as a product of two functions, so if we think about that as being x squared times 1 on the square root of x plus 2, okay, so we know the domain for that is r. For this function, now the square root means that x plus 2 could be bigger than or equal to 0, but if it was equal to 0, then you'd be dividing by 0. So x plus 2 has to be bigger than 0 in this instance, which means x is bigger than negative 2. The intersection of those two things, well, one is r, so it's really just about this domain. So the domain of g in this case is the intersection between r and negative 2 to infinity, which is just negative 2 to infinity. Okay, the work for today is on a worksheet found in Appendix C of your booklet.